In the last video, you were very patient while I reminded you of the rules for how many significant figures were in a number. That's a bit of a theoretical concept, but here we get the payoff. The reason why we want to know how many significant figures are in a number is so that we can know how many to carry through a calculation, and therefore we can get some sense of the uncertainty in a calculated result. Remember, that's what significant figures are for, to give us a measure of how uncertain the result is, how many digits we can trust the answer to. It turns out there are different rules for different operations. First, we're going to look at the rule for adding and subtracting measured values. And I've got a kind of an artificial example here. Suppose these masses were the masses of different packages of hamburger. You wanted to get a larger total mass of hamburger. We want to calculate what the total mass of hamburger is. Now that's a silly question, because what kind of grocery store would sell you hamburger with 3 different numbers of decimal places, 3 different precisions in the measurements? I don't know, just bear with me and we'll add this up. Now I'm a scientist, I always have a calculator with me. You should always have a calculator with you at all times too. I have a Texas Instrument calculator with me, and I'll try to guide you through using that a little bit, but you can also have a Casio or a Sharp calculator. If you're not familiar with it, maybe that's one of the things we'd like to talk about in our weekly group sessions where I can see you over Zoom. So if I take those numbers and add them up with my calculator, 2.5 kilograms plus 1.64 plus 0.253, and of course the calculator can't handle the units. Maybe I'll pause and you can see if you get this number first. All right, if you look at your calculator screen, it says 4.393 kilograms. The calculator doesn't say kilograms, but I know to include my units there. The question is, can I trust every one of those digits? And that doesn't seem very likely at all. If I only knew the mass of the first package to the nearest tenth, it doesn't seem likely that I could know the mass of the total to the nearest thousandth. Now what I'm doing here is a habit that I came up with myself. I don't know where I got this from, but you're welcome to use it. What I do is I underline the last significant figure, which you remember by definition is the uncertain digit in the measurement. And if I were adding the long way, as I did in elementary school, I would see that if I added down the columns where the numbers were lined up with the decimal points one above the other, if I add up a column that has an uncertain number in it, the result will be uncertain. So for example, because the 3 was uncertain, this 3 in the result is uncertain. And again, because the 4 in the hundredths place was uncertain, the hundredths place is uncertain. And because the tenths place was uncertain in this, the tenths place in my answer is uncertain. So this underlining, I've put an underline under every uncertain digit. You remember that significant figures mean all the certain digits plus the first uncertain one. So that means I'm going to have to limit my answer to the tenths place. So when I round this off, that would be 9.4 kilograms to the nearest tenth. We'll review the rounding rules in a few slides, but I bet you could have done that without me doing that first. So based on this example, I can write down the conclusion. We won't want to do this the long way every time. It turns out that when I'm adding, subtracting, the rule is that the result ends in the same decimal place as the measurement with fewest decimal places. The result ends in same decimal place as measurement with fewer decimal places. Here's another way to say the same thing. The measurement with fewest decimal places is the measurement that is least precise. So the precision of my result is limited by my least precise measurement. My experience working with people coming out of high school is that this is the less familiar of the two rules for carrying significant figures in calculation. So you may have to concentrate a bit on getting this one down. But remember, the value is there. These digits truly are significant. In other words, in this particular case, I can't trust the result here to more precision than the measurement that I did. I wouldn't make sense to try to give you that value to the nearest thousandth. So let's look at another example using the rule for addition and subtraction. Every time I go on to a new example, I try to throw another little twist into it. This time we've got scientific notation. Now I'm going to do this on my calculator, and as I say, I've got a Texas Instruments, but I can show you how to use your own calculator. For scientific notation, I would put in 3.543, and instead of the times 10 to the fourth, I would hit on my calculator EE. So far I've punched in 3.543 EE, and that brought up on my display two little zeros as superscripts to my number. That's the space for the exponent. So because this was 10 to the fourth, I'm just going to put in 4. And what my calculator display looks like now is 3.54304. You don't put in the times, you don't put in the 10, you just hit EE4. My calculator has EE for scientific notation. Yours might have EXP. That's what I see on other calculators. Okay, so that's in my calculator memory, and now I'm going to subtract the other number in scientific notation, minus 2.1 EE3. And what my calculator display says is this. Now that's the numerically correct value, but the calculator's not as smart as I am. It doesn't know where to add and the number of significant figures. Do I trust all of those threes? Remember that the rule for significant figures when I'm subtracting is that my result is limited by where the measurements end, where the last digit is. I can't compare them directly when they're in different powers of 10. To see what's going on, I'm going to have to put them both into the same power of 10. Maybe I'll turn them both into powers of 10 to the fourth. So here's the first number. It was already times 10 to the fourth. We'll just leave that there. And now I'm going to stack one under the other, just like I did the long way on the previous slide. I've got to turn this into 10 to the fourth to have a meaningful comparison. When I look at this number, I just made the exponent bigger by a power of 10, so I'm going to have to make the number smaller by a power of 10 to compensate. In other words, that's 0.21 times 10 to the fourth. And now, if I do the subtraction, here's my last uncertain digit in each one. On my calculator, that would come out to be 3.33, but because this was uncertain in the thousandths place, this is uncertain. Because we had uncertainty in the hundredths place in this one, this is uncertain. And the tenths and ones places are certain. Significant figures are all the certain digits plus the first uncertain one. So that tells me that it's the first three threes that are significant. In other words, back to the value here, that's my last significant digit. So before I have my final answer, your final answer must always be with the correct number of significant figures. I'll be watching for that every single time. That's the correct answer, but I could have written it in scientific notation. Whoops, make that complete here. To me, those are exactly the same number. Which one's the right one? They both are. When you're doing work for me, as long as you meet the conditions of the question, you're fine. I didn't specify whether I wanted scientific notation or not, so either one of those answers is just fine. And those are the rules for adding and subtracting. So moving on to another kind of operation. We've got another rule for significant figures carried through a multiplication and division. And again, I've got an example here to set you up. I want to calculate the volume of this rectangular solid. And you'll remember that volume is length times width times height. Now, in this case, I'm going to fill in the numerical values for the length and width and height. And I'm modeling for you what I hope is good problem-solving strategy. I want to write an equation to show what the main idea is. Whether or not you show that is really up to you for a simple case like this. But I do want to see for everybody's calculations that they hand in to me that you've got the numbers from the raw data along with the units. Units are always included with a measurement. It's not just because I'm anal, but because the unit tells me the meaning of the measurement. Because that measurement is in centimeters, that tells me I'm looking at a unit of distance, in this case, length. Now the width, do I care which one I call the width? Not really. 2.54 centimeters times 5.920 centimeters. And again, this is a bit of a funny question. Why would I be using a ruler that measured some of the measurements to the nearest hundredth and then picked up a different measuring instrument and read it to the nearest thousandth? Well, in this scenario, we assume that the digits were recorded correctly. I've underlined the last significant digit, the uncertain one in this case. Now, I can tap that in on my calculator and pause the video so you can beat me to it. Anything you do before I get there, that means you own it and you don't have to think about it later. All right, so we're back from that calculation and my calculator says 2.02.094592. I also know that I have to include units in all my work. Centimeters times centimeters times centimeters is centimeters cubed. And that's reassuring. I don't just put units on because I'm anal. Again, the units give me a sense of the meaning of the number. Cubic centimeters is a unit of volume. And that's reassuring. I can't guarantee that it means I did the question right, but it's better than if I hadn't got a unit of volume as a result. So we've got the units. Now, you're probably not surprised that we're not going to trust all of those digits. To what measurement can I trust that volume? What we could do is do multiplication out the long way, like you learned in elementary school, and again, follow the uncertain digits through the calculation, but that would be really tedious. Just let me tell you that what the rule turned out to be. For multiplying and dividing, the result has the same number of Sig Figs as the measurement with fewest Sig Figs. That's a different rule than it was for adding and subtracting. In adding and subtracting, we cared where the number ended. We didn't care how many significant figures it had. For multiplying and dividing, we care how many significant figures are in each measurement. And I suspect that's the rule that's more familiar from high school. Now, it seems like I'm just making up these rules out of nowhere. Actually, these rules can be derived using calculus. And that will come up with some rules that are really much more accurate than what we're doing here. In physics class, you may actually have done what's called propagation of error using the formulas that came from calculus. That's much more accurate. But that's slow. So what I like about these rules for significant figures is they're pretty quick and give us a reasonably good estimate for the uncertainty in a measurement. So in this particular case, let's see how many digits we should keep. In 13.44 centimeters, I see 4 significant figures. In 2.54, I see 3 significant figures. And in 5.920, I see 4 significant figures. Trailing zeros are significant if and only if there's a decimal point in the number. And because there's a decimal point here, that trailing zero is significant. There are 4 significant figures. 4 significant figures times 3 significant figures times 4 significant figures, it's going to be 3 significant figures. So I'm going to round off my volume after the 3rd digit. My hardest pitch with significant figures is convincing people that they truly are significant. But again, let me remind you the bigger picture. When we get this answer of 202 cubic centimeters, what's that's telling me is that I can trust that volume to the nearest 1 cubic centimeter. In other words, the true volume is somewhere between 201 cubic centimeters and 203 cubic centimeters. All right, let's step it up a little bit. We've got some scientific notation here. And again, I'm going to pull up my calculator. Pause the video, calculate this for yourself, and see what you get to the correct number of significant figures. Remember, anything you can do before I get there, that means you own it and you don't have to do it later. All right, pause now. So we're back, and what I see on my calculator screen is 196,219.5122. Because I'm dividing, I need to see how many significant figures there are. This number has 4 significant figures, and this number has 3 significant figures. Leading zeros are never significant, they're just placeholders. We're limited by the number with fewer significant figures. We're limited to 3 significant figures. So I've just underlined the 3rd digit there, rounding it off to the nearest thousandth. It's 196,000. And that is the answer. I'm not going to say approximately equal. To a chemist, that is equal. That's the difference between a physical science and math. In math, you can work with exact numbers, but every measurement we make has measurement uncertainty in it. So within the limits of our measuring instrument, those values are equal. Now that's a perfectly good answer, or I could have put it in scientific notation, but again, it's got to have only 3 significant figures, no more, no less, when I do it in scientific notation. My last thought about this calculation is I hope you didn't waste time putting those 2 numbers in the same power of 10 as we did in the example for adding and subtracting. I don't need the numbers lined up when I'm multiplying and dividing. I can see how many significant figures there are either way. It's only when you're adding and subtracting that you need to put them in the same power of 10 so that you can meaningfully line up the decimal places. Okay, let's ratchet it up one step more. The next example has 2 operations in it. And we're going to follow the order of operations from math class. I learned about BEDMAS, brackets, exponents, then division and multiplication, then adding and subtracting last. So I'm going to first do what's in brackets here, and I'm going to write myself a nice clear solution, one step at a time. Go ahead and figure out this calculation. I'm going to pause, and when we come back, I want you to have the final result with the correct number of significant figures. So we're back, and I did the brackets first. So in the numerator, I got 0.798, and we're still dividing by 18.9, 118.9. I've got to put that number there to keep the equation true. That equal sign is loaded with meaning, and what that means is the 2 sides of the equation are exactly the same. So I've got to show that 118.9 as well. Now the reason I'm doing this a step at a time is that there's 2 different operations, two different kinds of operations with two different rules for significant figures. First, I did a subtraction, and in subtraction, I worry about where the number ends. This ends in the thousandths place, this ends in the hundredths place, so I'm limited to the hundredths place here. So now when I go on to the next step, I've got that full unrounded value in my calculator display. Now I'm going to divide by 118.9, and my calculator says 0.006711522. That's the last time I'm going to write out my full calculator display. That seems like a lot of writer's cramp to me. From now on, now that we know the rules for significant figures, I'm just going to show the result with the correct number of significant figures right away. When you're showing your solutions to me, you can use some judgment. Write yourself enough detail that you're absolutely clear about your solution, that you're confident that you've got to the right answer, but don't bother showing me things you don't need to show yourself. What I need to see is the original starting numbers and the results with the proper significant figures. In the intermediate stage, you can show more significant figures than are valid, as I did here, or you can show it rounded off in the intermediate step. This would be 0.80 if I chose to do that. I would, however, keep the unrounded value in my calculator because I don't want round-off error. And I would certainly not express that as 0.8 because that would be too few significant figures. Once you lose significant figures, you can't get them back. So if I ever catch you throwing significant figures away mid-calculation, I'll get you. Okay, so I found the significant figures in the 0.798 using the rule for subtraction. Now I'm going to forget its history and do the division. I've got the full 0.798 divided by 118.9. That's two significant figures for the numerator divided by four significant figures. So I should have only two significant figures in my answer, and my final answer is 0.0067. Or you could have expressed that in scientific notation. Either is fine. So we talked a little bit about rounding in some examples. Let me refresh you on the rules you learned for rounding in high school. Let me remind you that I think memorizing is evil. And the reason I think it's evil is because it doesn't work. If you thought you needed to remember rules that you memorized for rounding in high school, you might think you didn't know how to do this now. We don't want to memorize rules. We want to think about why they apply. So instead of listing off rules, I'm going to tell you the spirit of rounding with this example. So in the first example A, the question is to round it to two significant figures. In other words, we need it to stop at the second digit. The spirit of rounding is this. It is obvious that that number is between 2.3 and 2.4. Your job is to estimate which one it is closer to, 2.3 or 2.4. In this case, it's quite obvious that it's closer to 2.4. Now, you might have learned a rule in high school that said when the digit you're going to drop is greater than 5, round up. Well, yes, that's true. But did you need to remember that? No. All right, on to the next one. I'm only going to pause briefly while you record the value to two significant figures. I'm going to ramble while you think about it. That number is definitely between 7.2 and 7.3. So to two digits, that is 7.2. It's closer to 7.2 than it is to 7.3, right? Now, you might have learned a rule that if the digit you're going to drop is less than 5, round down. Well, yeah, but I didn't need a rule for that. All right, on to C. And again, you're going to round it to the second digit, to the second significant figures. Okay, you got ahead of me there. Is it closer to 2.85 or, sorry, is it closer to 2.8 or 2.9? By a smidgen, it's closer to 2.9. So that's the correct rounded value. Okay, on to D. Is that number closer to 2.7 or 2.8? We've got a dilemma here. It's equidistant between 2.7 and 2.8. And there are two rules that I know. I don't care which rule you pick. Both are widely used, and I would never tell you you were wrong for doing something that's widely accepted. The rule you might have learned from high school is that if it's a 5, round up. And if you were going to do that, that's fine. But let me tell you the rule I learned when I was an introductory chemistry student. What I learned was when the digit to be dropped is exactly 5, we're going to round to the nearest even digit. Now, I don't want you doing anything just because I say so. I don't want you accepting authoritative knowledge. Let me tell you why that works. The reason I like that is that sometimes it means I'll round up, and sometimes it means I'll round down. So when I have a large collection of numbers and I wanted to average them out, the times I round it up and the times I round it down should cancel each other out, and I won't get a systematic error when I'm done. So using that rule, D would be rounded, it's between 2.7 and 2.8. 8 is the even digit. I'm going to round it to 2.8. Those of you who had the rule to round up when it's exactly 5, you would have 2.8 as well. The difference comes in E. That number is between 2.8 and 2.9. The even digit is the 8. I would round that to 2.8. Although those of you who are consistently using the rule of rounding up if it was exactly 5 would correctly have rounded it to 2.9. Doesn't worry me too much. Significant figures are plus or minus 1 in the last digit anyway. Now the last slide for this video talks a little bit more about precision and accuracy. Oops. And that's moved off to the side a little bit. I don't know. All right, let's just work with that the way it is. We've been talking in significant figures. We've been talking about precision. How much I can trust that number to, how many decimal places I can trust that to. Another way to describe precision is as the reproducibility of a measurement. If I make multiple measurements and they're very close to each other, I would say that my measurements were reproducible. Another thing we want our data to be is accurate, but that's not the same thing as precision. Precision talks about how close your measurements are to each other. Accuracy means agreement with the true value. And I'm going to put true value in parentheses there. Sometimes we know the true value and sometimes we don't. My husband is an analytical chemist at Tech, and they measure, say, the concentration of lead in river water. How do they know what the true value is? They have ways. They have other labs that come in periodically and test the same sample, but who says they've got the true value? So that's why I've got true value in quotation marks. Sometimes we never know which is true. Now, ideally, we want our set of measurements to have both precision and accuracy. These pictures help you see a visualization of what's different. What we want is the scenario in A. It's both accurate, those shots are on the bullseye, and they're precise, they're close to each other. But in B, If the darts are shooting at the bullseye, these results are close to each other. They're precise, but they're not accurate. They miss the bullseye. They're not close to the true value. And C is the worst case. They are neither accurate nor precise. They're not on the bullseye, and they're not close to each other. Some related terms for this is random error and systematic error. We want to control random and systematic error to help guarantee as much as possible precision and accuracy. Random error is just because you never get exactly the same reading exactly twice. If I had two of you reading the measurement on the graduated cylinder the other day, for example, one of you might say 26.2, one of you might say 26.3, one of you might say 26.4. What I would do to get rid of the random error is average the results to cancel out some of that random error. In other words, I could improve my precision by averaging the results. At random, somebody be a little too high, somebody be a little too low, and when I average them, I get a better estimate. Systematic error has to be controlled to have good accuracy. And one kind of systematic error I can think of, when we weigh things in the lab on the balance, it should say 0 on the digital balance before you put the object on the weigh pan. Sometimes it doesn't, in which case you would have to hit the tare button, T-A-R-E, tare, to get it go back to 0. But if you didn't hit the tare button first, if it was a non-zero reading, then every one of your weighings would be off by that value. We want to get rid of that kind of error. Not tearing the balance is a systematic error. We're going to try to eliminate those to improve accuracy. If you've ever found a source of error in your experiment, you were identifying a source of systematic error, probably. All right, that's enough on significant figures for now. Remember, significant figures are not the most important thing. They are just the icing on the cake, but we're going to ice every cake. We want to get these skills taken care of early. We want to get these rules to the back of your mind, never at the front, but always at the back.